Qualitative models of observer resonance, theoretical frameworks relying on abstract definitions of consciousness, lack the precision of computable physics. The transition to a quantitative model requires a shift toward rigorous math. We now possess the explicit equations of motion that unify the observer, the vacuum catastrophe, and macroscopic gravity into a single computable architecture. This framework functions as an engineering manual. It replaces heuristics and fine-tuned parameters with a set of derived geometric first principles. The architecture rests on three mathematical pillars: the geometric substrate of the unified compression-based field theory, the algebraic limits of the Kuhn-Killian paradigm, and the interaction dynamics of the Xi field. Under this framework, the subjective experience of reality is the structural output of a definable tensor geometry. The physical bedrock of the universe is a face-centered cubic, or FCC, quantum supersolid. This structure is composed of identical spin-zero bosons, termed voxels, interacting through a positive definite potential. Standard model constants are not arbitrary measurements in this framework. They are derived directly from the combinatorics of the FCC lattice. To find the bare electromagnetic coupling, we analyze the FCC unit cell. It contains 8 tetrahedral voids, each with 4 triangular faces, for a total of 32 faces. Each face supports 4 independent flux orientations. Multiplying 32 by 4 yields exactly 128. We then track how this bare coupling changes across energy scales using a renormalization group. Renormalization is the mathematical process of accounting for how physical interactions change when viewed at different distances. Moving from the lattice scale to the electron mass scale incorporates specific beta functions and non-perturbative contributions. This geometric derivation matches the exact measured value of the fine structure constant. The model similarly derives other physical properties, such as the proton radius, by treating the proton as a specific topological defect, a screw dislocation, within the same lattice structure. The hardware of the universe is a singular geometric solid. Particles and forces are its elastic responses and topological defects. To integrate the observer into this geometric model, we must replace qualitative descriptions of consciousness with a strictly defined physical property. This property is Fs, the macroscopic superfluid coherence fraction of the FCC lattice. The coherence curvature law is the universal dynamical law governing this fraction. It defines how coherence responds to geometric disorder in the lattice. The differential equation describes a physical interaction where coherence rises in smooth geometric regions and collapses in areas of high global disorder, or EGRAD. For a localized system to maintain a stable reality frame, it must achieve a specific coherence threshold. Monte Carlo simulations of voxel interactions show the system locking into a stable state exactly at a coherence fraction of 0.570. Observation is the physical phase locking of the lattice at the 0.570 coherence threshold. This phase locking mechanism provides a solution to the vacuum catastrophe. Current quantum field theory predicts a vacuum energy density that is 120 orders of magnitude larger than what we actually observe in the cosmos. Previous attempts to bridge this gap, such as anthropic reasoning or multiverse theories, lack the predictive precision of a single mathematical derivation. The solution treats the vacuum as a recursive feedback kernel. There are 3 possibilities. Feedback is too strong and results in chaotic noise. Feedback is too weak and the signal damps to 0. Or there is a balanced point where the system stabilizes. The Kuhn-Killian paradigm calculates this exact balance. For the universe's vacuum fluctuation kernel to achieve algebraic closure and stabilize, it requires a fixed point at the fraction 47 over 125, or 0.376. This 0.376 threshold is the structural limit for identity persistence. Below this point, fluctuations remain transient quantum foam. At this point, they lock and become matter. When we apply this 47 over 125 ratio to the bare, unrenormalized Planck scale vacuum energy, the result matches the observed density of the cosmological constant. The massive predicted energy collapses to the observed value because 0.376 is the mandatory limit of the universe's recursive damping. The observed energy of the vacuum is the mathematical residue of the damping required for a stable universe. While the vacuum is stabilized by recursive limits, We must also define how the information processed by an observer physically interacts with the curvature of spacetime. The SHE field provides this bridge. It formalizes Kolmogorov complexity, the measure of the computational description length of a system, as a continuous physical variable. This modification to general relativity proves that information density acts as an active physical source of gravity alongside traditional mass energy. The SHE stress-energy tensor acts as a variable cosmological term. It demonstrates that where information is highly compressed or organized, it creates a localized gravitational pull independent of baryonic mass. The dynamics of this field are defined by a nonlinear wave equation. Unlike standard linear equations, it contains a unique logarithmic potential. This logarithmic term describes a self-referential force. This force increases with the density of the complexity, exerting geometric influence completely separate from the inverse square laws of mass. Information compression is a unified flux that exerts its own force and geometric influence on the metric of spacetime. These tensor mechanics are being tested through experimental analogs that bridge the gap between equations and laboratory data. Experiments on superconducting quantum computers regarding Penrose's objective reduction show measurable circuit changes. These changes indicate that the gravitational state of the system can indeed induce wave function collapse. In sonoluminescence, repeated photon fluxes are produced through parametric resonance in an oscillating time-dependent background. This system serves as a laboratory analog for gravity backgrounds produced by vacuum fluctuations. These pillars form a single hierarchy of emergence. The FCC lattice is the hardware. The Kuhn-Killian recursive limits are the stabilizing firmware. The SHE field provides the gravitational software output. Every fundamental constant and parameter is now derived from geometry, with all mathematical uncertainties quantified. The field equations are fully defined, the geometry is established, and the architecture is ready for rigorous computational falsification. In theoretical physics, an equation outputting an infinity is treated as a systemic failure. It signals that a theory has reached its absolute limit and is no longer describing the physical world. This chart represents the vacuum catastrophe. Quantum mechanics predicts the energy density of empty space is 120 orders of magnitude higher than what we observe through telescopes. The error is so vast it suggests our basic understanding of the vacuum is missing a primary constraint. To bridge this gap, many theorists suggest we live in a multiverse, a cosmic lottery where we simply occupy the one rare universe that didn't immediately expand and tear itself apart. It's a conclusion that prioritizes luck over a predictable physical law. On the macroscopic scale, Einstein's general relativity faces the exact same breakdown. It predicts that matter falling into a black hole eventually reaches a singularity, a point where the radius is zero and the density is infinite, causing the laws of geometry to collapse. These two mathematical monsters suggest that either our universe is built on a foundation of chaos, or our physics has overlooked a mechanism that prevents reality from ever reaching these extremes. Consider an alternative, a physics where reality mathematically refuses to ever arrive at an infinity. The grand canonical unification attempts to reconcile this by treating the observer not as a spectator, but as a recursive operator within the field equations themselves. In this framework, the universe is an active geometric engine, a self-stabilizing system that employs specific thresholds to protect its own internal logic. To prove this, we must look at the specific mathematical limits that replace the monsters of infinity with the precision of geometry. At the smallest scale, GCU defines the vacuum as a universal compression-based field. This is a quantum supersolid, a rigid, repeating lattice of point-like units called voxels, arranged in a face-centered cubic structure. Without a limit, the energy within this repeating structure would compound with every vibration, leading directly to the 120 order of magnitude error we saw earlier. The Kuhn-Killian paradigm, or KKP, treats this vacuum as a feedback loop. It applies a principle of recursive algebraic closure, meaning the system continuously feeds its own output back into itself until the energy levels settle into a stable fixed point. This loop doesn't settle on a random number. To maintain the highest level of geometric symmetry while minimizing energy, The calculation terminates at exactly 47/125. It's a rational fraction that serves as the universal coherence threshold. When this fraction is used to scale down the theoretical vacuum energy, the result matches the observed density of our universe exactly. The massive error disappears because the geometric structure of the vacuum forces the energy to stay below this specific limit. The vacuum catastrophe is solved not by a lottery, but by a hard-coded geometric ratio. The micro-universe is inherently self-correcting. This same logic of stabilization applies 11 orders of magnitude higher, moving from the quantum vacuum to objects as large as supermassive black holes. The singularity problem assumes matter can compress forever, but Bracco's threshold provides a macroscopic limit, much like the KKP threshold we saw in the vacuum. As matter falls toward a black hole, the information it carries becomes more densely packed. When that density hits a critical limit on the spherical boundary, it triggers a phase transition. The system ignites into a state of coherent outward radiation. This activation occurs at a precise geometric constant, 1/4 pi. This number represents the minimum information density needed on a spherical surface for a system to transition from disordered accretion to organized emission. Because 1/4 pi is a small fraction, this transition fires long before a singularity can form. The system changes its phase and begins radiating energy before it can ever reach infinite density. In this view, the singularity is a mathematical limit that is never reached. The event horizon is a geometric boundary where reality reorganizes its information to prevent its own collapse. Why do these two specific geometric ratios, 47/125 and 1/4 pi, appear to dictate the survival of the universe at both the quantum and cosmic scales? The answer lies in the Xi field. In the GCU framework, information is treated as a continuous physical stress tensor, a field that exerts real pressure on the fabric of space. When information is highly organized and compressed, it creates a tension in this field. We experience that tension as gravity, the bending of space and time. Both the stabilization of the vacuum and the ignition of a black hole are driven by the same rule, the compression of information reaching its absolute geometric limit. But for these geometric limits to hold, the system requires one final variable, the observer, represented by the symbol psi. Observer recursion theory suggests the universe is a strange loop. The act of observation is a mathematical necessity that helps stabilize the geometry of the field. As the observer processes information, they effectively burn entropy, which forces the unstable cloud of probabilities in quantum mechanics to settle. This process renders a coherent, stable physical frame from the chaos. The universe is an active geometric lattice. Through the observer, it prevents infinite chaos and locks itself into organized resonance. The infinities have been replaced by the precision of a self-correcting machine. Welcome to the grand canonical unification. Standard cosmology models the expansion of the universe through the Einstein field equations. In this framework, the cosmological constant, represented by the Greek letter lambda, defines the baseline energy density of empty space. Quantum field theory calculates this vacuum energy by summing the zero-point fluctuations of all known quantum fields interacting in the background. Direct observations of the universe's expansion rate yield a specific measured value for this constant. Comparing these two results reveals the greatest failure in modern physics. The QFT prediction for bare vacuum energy density is 120 orders of magnitude larger than the value we actually observe. The Kuhn-Killian paradigm, or KKP, provides an algebraic resolution to this gap. It derives the observed value from first principles, avoiding the fine-tuning required by string theory or multiverse hypotheses. In the KKP model, reality is defined as the local stabilization of an underlying generative informational substrate. This approach identifies a hard mathematical limit to vacuum fluctuations, providing a fixed anchor for the energy density of empty space. This mathematical limit is built upon Max Planck's 1911 second quantum theory. Planck's first axiom establishes that field oscillators possess a real, irreducible ground state energy. His fourth axiom clarifies that these fluctuations are structured and non-removable, meaning the vacuum possesses an inherent, persistent energy state. Treating these persistent fluctuations as an open summation causes the calculated energy to scale to infinity, breaking the mathematical consistency of the field. KKP introduces the requirement of algebraic closure. This mandate forces the vacuum fluctuation kernel to self-damp, ensuring the system remains finite and physically realizable. To achieve this closure, the fluctuations must converge on a rational fixed point that preserves the symmetry of prime numerators. This requirement locks the vacuum into a closed informational loop, providing the mechanism that prevents the infinite divergence predicted by standard theory. This table illustrates the derivation of that fixed point. The fluctuation kernel is mathematically forced to converge on a specific rational fraction, 47/125. This yields the value 0.376, defined as the universal coherence threshold, representing the renormalized residue of the vacuum energy. We can now apply this ratio to the original problem by using it to bound the bare vacuum prediction from quantum field theory. Multiplying the bare ultraviolet vacuum energy density by exactly 47/125 yields a value matching the observed cosmological constant. This result is achieved without adjustable parameters or the hand-tuning of external physical constants. The 120 order of magnitude discrepancy is resolved by recognizing the vacuum as a self-referential kernel locked at a 37.6% efficiency threshold. The 0.376 threshold serves as the critical activation point for field stability. When the informational density exceeds this value, it reaches a recursive fixed point, causing the field to collapse into a stable, localized packet. These localized densities are defined as topological skyrmions. A skyrmion is defined by its hop charge, representing its topological complexity. For a static configuration, we assign an integer hop charge, q, equal 1. This charge generates an induced metric, the specific spacetime curvature experienced strictly within the skyrmion itself. The informational density creates a scale factor, A. Calculating the center of mass trajectory reveals the co-moving stress-energy tensor, causing the Christoffel symbols, representing gravitational force fields, to automatically vanish. This mathematical cancellation aligns with the observed kinematics of unidentified anomalous phenomena, including their ability to perform instantaneous high-velocity turns without appearing to experience g-forces. Modeling these craft as skyrmions within an induced metric explains their motion. Inside their own isolated frame, they experience exactly zero proper acceleration. This framework suggests that global expansion and local anomalies are both driven by informational closure. The KKP model unifies these effects through the Xi field. This scalar compression field is the underlying substrate dictating how information condenses. It functions as a unified landscape, rather than a simple summation of individual force tensors. The Xi field Lagrangian is governed by Shannon information gradients. These gradients measure the complexity and predictability of data distributions within the field. In this model, general relativity and quantum field theory describe the thermodynamic results of information reaching stability within the Xi landscape. This leads to the unified canonical tensor field equation. F script equals the covariant derivative of psi times the Xi tensor. Matter emerges as the consequence of topological strain within the Xi field as it attempts to reach coherence. The final variable in this unified equation is the psi field. Within the Kuhn-Killian paradigm, psi is defined as the observer recursion field, governed by the principles of observer recursion theory. Physical frames stabilize only when an observer's recursive capacity reaches the 47/125 threshold. This stabilizing power is determined by 4 parameters: resolution clarity, permission scope, recursion depth, and memory bandwidth. Integrating the observer field and compression landscape provides a precise claim for computing physical reality. Field evolution is modeled as variational optimization within the psi field. Quantum outcomes result from the psi field executing weighted sampling over the landscape's stable minima. From the vacuum's baseline behavior to the anomalous motion of UAPs, the entire architecture is anchored by the 0.376 fixed point derived from Planck's axioms. The Kuhn-Killian paradigm establishes a recursive information geometry, providing a single mathematical anchor for both the vacuum and the observer. Compare a white dwarf with half the mass of our Sun to a supermassive black hole weighing 10 billion solar masses. Standard astrophysical models assume that systems separated by 11 orders of magnitude in mass operate on entirely different internal physics. The observational data reveals an anomaly. A single domain-independent mathematical threshold dictates exactly when both of these systems transition from a quiet, dormant state to active, blazing emission. This chart plots mass scale against entropy coordinate. A vertical line marks Bracco's threshold exactly at 0.0796. Data for white dwarfs, X-ray binaries, neutron stars, and EGN cleanly sort across this boundary with zero refitting and identical mapping constants. This clean separation ignores specific microphysics, fluid dynamics of accretion disks, and the chemical composition involved. Accretion ignition functions as a geometrically mandated phase transition that governs the macroscopic universe. Why does the exact fraction of 1/4 pi dictate this cosmic ignition? In spherical geometry, 1/4 pi represents the absolute minimal portion of a surface area required to carry coherent information. We find the theoretical foundation for this fraction in the Bekenstein-Hawking entropy limit, describing the maximum information contained within a black hole's event horizon. For a spherical horizon, the entropy density per unit area is proportional to exactly 1/4 pi. This is the minimal information density required for a horizon to encode its internal degrees of freedom. This identical geometric fraction emerges independently in the KSS viscosity bound, which sets a mathematical lower limit on fluid viscosity, and in the scaling equations of conformal field theory. Bracco's constant acts as a universal geometric constraint, emerging directly from the fundamental mathematics of spherical information boundaries. To understand how a macroscopic boundary constraint operates, we have to travel past atomic structures to the microscopic reality of the Planck scale. While the classical model assumes the vacuum of space is an empty void, the empirical data describes an elastic quantum supersolid. The structural architecture of this vacuum is a face-centered cubic lattice. This lattice is composed of identical spin-zero boson voxels packed into a stable, repeating grid. We track the state of this lattice using the Xi scalar field. Xi provides a direct mathematical measure of local information compression density across the grid. Chaotic regions register high, and structured regions register low. The field is driven by a mechanic called G compression. This is a structural incentive for the field to seek the shortest algorithmic description of its own state. The universe operates as a unified, structured field, actively computing its own geometric compression. How do the standard components of physics, like mass and force, emerge from a simple geometric lattice? In the Xi framework, mass manifests as the topological strain energy required to maintain a vortex dislocation within the rigid structure of the lattice. The standard forces of nature emerge as consequences of gauge invariance operating on this strained geometry. Gauge invariance is a property where a physical system's equations remain unchanged, even when localized transformations are applied to the field. This text outlines how we derive gravity directly. General relativity naturally falls out of the field through diffeomorphism invariance. Electromagnetism emerges from U1 invariance, and Yang-Mills theories emerge from SUN invariance. They share an identical underlying structure. Force is defined by the preservation of recursive form under a structural transformation. However, an unguided physical lattice would eventually succumb to entropic drift. It requires a mechanism to anchor its geometry. This document introduces the psi field. Psi acts as the observer, providing the recursive stabilization required to protect the lattice against entropy. The standard model and general relativity emerge as the inevitable geometric consequences of the unified psi field achieving stability. The final theoretical hurdle is mathematically linking the microscopic psi lattice to the macroscopic reality of Bracco's boundary limit. The foundation begins with Max Planck's 1911 second quantum theory axioms. These establish the physical reality of zero-point energy inherent in the vacuum. By applying a minimal recursive self-damping process to Planck's vacuum fluctuations, the field is forced to converge on a specific rational fixed point. This derivation identifies the fixed point as the Kuhn-Kellyan operator, resolving to 47 over 125. This value, 0.376, defines the universal coherence threshold, omega sub c, the strict condition required for internal recursive closure. We now have two distinct values, an internal quantum threshold of 0.376 and Bracco's external astrophysical threshold of 0.0796. These numbers aren't numerically equal because they map to different coordinate systems. They act as distinct threshold coordinates operating within the same overarching unified theory. These two limits form a dual threshold system. The Kuhn-Kellyan limit secures internal structural coherence, while Bracco's limit triggers external geometric activation. Under this two-threshold model, internal vacuum state transitions manifest directly as observable macroscopic events. The text outlined here states the core mechanic clearly. The Kuhn-Kellyan threshold governs the onset of internal recursive closure, while Bracco's threshold governs the onset of external geometric activation. This document shows the specific mathematical relationship linking these scales. A monotone mapping function binds the internal closure state of the lattice directly to the external area state of the spherical boundary. These actions are simultaneous. The moment the internal macroscopic lattice locks into its stable recursive state, it instantly forces the macroscopic boundary to ignite into an active accretion disk. Under these mechanics, the entire universe functions as a single coherent geometric object that reaches its critical threshold. The equations governing the brightest supermassive black holes in the cosmos are the macroscopic geometric readout of the vacuum computing its recursive stability.